Yeah, so I'll be talking about compound data embeddings, how to handle text plus graph data. And this is joint work with my advisor Ravi and another one of his PhD students, Tanay. And this was done while we were interns at Amazon. So I'll first give a concrete problem, and I'll then explain our approach and the performance we get. And then I'll, towards the end, I'll talk about the general setup and some theoretical justification that we are currently working on. So the problem is we are on an e-commerce website, the user makes a tail query, but that doesn't yield any products. So a tail query is a query that the search engine doesn't see often. Those are the very infrequent queries. And two common reasons why you may not get any results are because the query is too long or too specific, or it's just too vague. And the existing solution that is often used is you drop a few words and see if that starts giving results or not. So an example of that happening is if you search for red and black, blood, knife, snake eye, there's a typo, it should be red and black. So, and this is a very specific query. They're actually looking for a knife with a particular design and so on. And what is done is you drop most of the words and you search for red, blood, knife, which gives you a book and curtains and whatnot. So the main problem is, can we do something better? Can we, instead of just randomly dropping these words, can we reformulate this long query into something that will give better results? And an example of that would be if you instead search for knife, snake eye, red, black, you'll get the knives that were actually the user was actually searching for. So more formally, the problem is that you want to learn a model that infers related queries given a new test query text. And so while training, you'll have access to query product behavior, which you use to get a query graph, which is, so every node in the graph will have the query text as words, as the node labels, and you add an edge between two queries if they share any product. So if you search for an iPhone and you search for two different queries, iPhone-related queries, both resulted in someone buying an iPhone, then both of those queries will have an edge between them. So this is while training. You'll have all this past data about searches, but during inference, you only have a new query text. You don't know the related queries. So you don't know the edges that the new node will make to existing nodes in the graph. And that is what we are trying to solve. So, and the basic approach we are using is we are going to come up with embeddings such that related queries will end up being closed in the embedding space. So the two iPhone related queries that the example that I mentioned, they'll end up being closed in the abstract real vector space. And now, since we're going to be using embeddings, I need to explain why existing methods do not work. So since we are working with text, you may think that we can use word or sentence embedding methods somehow, but the issue is the relationship between queries is coming from the graph. So word embeddings will, you get word embeddings from a corpus which has no relation to the purchase behavior of users. So word embeddings will not help you there. So things like word to vec or glove will not help. And if you think that we'll take individual words and use them to get a sentence embedding where the query is the sentence, even that sort of starts failing because, so for example, if you have two queries like say fidget spinners and anxiety toys, those two are actually related queries because anxiety toy is, it's because fidget spinners were marketed for anxiety, so anxiety toy is also a query that should result in fidget spinners showing up, but no word embedding or sentence embedding is going to capture that. So essentially, none of these things can incorporate graph data. Now, since we have graphs, if we think that graph embeddings will work, again, all graph embedding methods, the simple problem there is, if you want to do inductive learning where you are given new nodes and you want to come up with embeddings, the problem that existing graph embedding methods face is that they need the edges of the new node. And so if you can give the edges of the new node, you will get an embedding, but that's our whole problem. We don't have the edges of the new node. So, which means that now these methods are useful. Naive idea you can think of is that you start with graph embeddings and then you perhaps train an LSTM to map your query text to these embeddings. So the LSTM will learn to go from the text to an embedding. We tried this, but there are two main problems. One is that LSTMs are quite slow to train. When you have hundreds of thousands of queries, the training starts becoming really slow. Plus, empirically, this doesn't perform too well because we noticed that LSTMs tended to overfit to the text part of it instead of really getting the graph behavior. So those are two problems that this kind of an approach faces. So then the better approach is to use an attention network to generate the text embeddings, and the graph information is only present in the loss function, which means that it is only used while training. So the same network, we can use it during inference, and that will go from text to an embedding. And since it has learned to sort of mimic the graph, the new queries will also hopefully match the unseen graph behavior. And once we have these embeddings, we'll just use k nearest neighbor search to recommend, say, 5 queries or something. So I'll talk a little more about the model. So attention, the whole idea of attention is that it will allow you to focus on the parts of the queries that are relevant. So for example, if your query is marble iPhone 7 32 GB case black, then you're actually looking for a iPhone 7 case, and the other things are not as relevant. The first thing the search engine should figure out is that it should focus on iPhone 7 in case. So it should pay more attention to those words and less to so 32 GB is completely irrelevant when you're looking for a case. It's internal feature, internal property of the iPhone, which is not useful. So hopefully an attention network will be able to ignore irrelevant things and focus on the relevant things. So the way we do it is we take the query as input as trigrams, so character level trigrams, and send that into an embedding layer, which will give us some vector for each trigram. We send those vectors into an attention layer, which will tell us that, okay, focus on iPhone, focus on 7, and focus on case. Ignore 32, don't pay too much attention to black or marble. And so we'll use those attention weights, take a weighted average of the trigram embeddings that we got from the embedding layer, and that's the final output. And the loss function is where the graph information comes in. We try the earlier idea where we try to match embeddings from a graph embedding method, so say node2vec or graph sage or something, and we just use cosine similarity to match node embeddings to those that were generated by the graph embedding method. The other method we use, the loss function we have, is we take negative and positive samples, which is to say that given a test query, we'll also pass in a lot of positive samples, which are related queries, and a lot of negative samples, which are queries that are different. So iPhone and fidget spinners would be, that'll be an example of a negative sample pair, while iPhone 7 and iPhone 7 32 GB would be positive samples. And then the loss function is basically trying to put positive samples closer and negative samples farther away in cosine similarity. And even within positive samples, we have two ways of doing it. One is from the query graph that I mentioned. You just uniformly sample your neighbors, and those become your positive samples. But issue with such a positive sampling scheme is that since we are trying to get the query reformulation to work for infrequent queries, the graph we have will be quite sparse. So if you keep uniformly sampling neighbors, you'll often end up just seeing one positive sample. But if you think about it, even things that are distance 2 or 3 away are also are related to the query. So another approach is to take long random walks, and any nodes that co-occur on long random walks become positive sample pairs. We'll see that this performs slightly better. And negative sampling is simply uniformly sampling a non-adjacent node from the graph. So if you put these two things together, you'll get some embeddings, but it's still not sure how you're going to measure how your model is. So how to measure the relevance of recommended queries is a issue we face. The primary reason for this is, again, the infrequent query tail query issue, which means that the data set is sparse. The graph is quite sparse. And plus, there is a lot of noise. So you may search for say an iPhone, but you may see a pen drive, and then you remember that, oh, right, I also want a pen drive, and you may buy it. And that information might get encoded into the data set. So the noisy and sparse graph is a difficulty in evaluating how good we do. And of course, the ideal measure would be to have a human sit and say, okay, you search for iPhone, blah, 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 and I think that these 5 queries are relevant. Am I correct? So the human is the best thing to use, but again, you'll have a problem where it's too expensive and too time consuming. So we use these weak signals of relevance. So let's say that we only give 5 recommendations. We'll look at the top 5 recommendations and see how many of them share a product with the test query. And then we look at all the products that were bought when you search for those 5 recommendations, and see what fraction of your test query products are actually covered. So the first thing is sort of precision. How correct are you in recommending these things? And the second is sort of diversity. You don't want to keep recommending the same kind of queries. You want to recommend diverse kind of queries. And the F1 is just the harmonic mean of these two, and you want to get a single number. So the first row is the theoretical best. We just ran a brute force thing and came up with the 5 recommendations that do best. As you can see, the difficulty is sort of visible in the numbers we get. The sparse data means that you don't get 2 good numbers. The rest of these are percentages. Attention is the standard attention model using trigrams. RW is where positive sampling is done using the long random walks. As you can see, you get a couple of percentage points better once you do the random walk thing. Instead of passing in trigrams, we tried passing in words, but that doesn't work as well as trigrams. And we think it's because words, if you pass in words as input, it cannot handle misspellings too well, while trigrams can handle misspellings. And this is the model where the loss function is trying to match embeddings from GraphSage, which is a graph embedding method, and they perform really bad. Our hypothesis is that the graph has too many clusters, so product clusters, product categories, and GraphSage is not able to separate out each of these clusters in its embeddings, and that is being reflected in even when we try, our attention models try to match that. Trigram hash is a simple text-based similarity measure which we use as a baseline, and we get almost twice as better as the baseline. or at least 1.5 times. I'll skip this in favor of time. And so now the general problem, you abstract out things. So instead of a query, you have a text, a general text, and edges will represent some relation between the text entities. And again, at inference time, you'll only have the text available. You don't know the edges to the already seen nodes. And the embeddings that we get should mimic this underlying graph. And so if you know word to vec, then this is saying that the co-occurrence idea from word to vec is being replaced by edges in the graph. And a few other concrete problems would be if you have queries and product titles and you want to go from queries to products or vice versa, instead of reformulating queries, you could do product titles and recommend related products. For example, Amazon gives you this other users who bought this also viewed and so on. Another thing is if you have tweets, then you can try to predict original authors of new tweets or unseen tweets. And the graph in this case would just be a collection of cliques with one clique representing one author's tweets. And similarly, you can do this with Stack Overflow titles, and you can recommend other questions. So we have some theoretical justification for why the attention works. Pardon the sort of crappy looking diagram, but the assumption we have is that these black dots are trigrams. They're assumed that you are using a two-dimensional space, and your trigrams sort of get mapped isotropically. These diamonds are your sort of concepts or product categories. So they may be Samsung phones or iPhone cases or iPhones. And these other shapes are your queries. And the generative model for coming up with a query is user will think of some thing that they want to buy. Say they want to buy an iPhone, and so then they'll do a diffusive walk around iPhones on the trigram vectors around iPhone, and at some point they'll stop, and that is your query text. Now we think that once you decide on a product category, the trigrams sort of get modified a little. So for example, black is something that you may have black iPhones, but you may not have black iPhone cases or something like that. So black may get pulled or pushed away from a category, and depending on that, you may get your chance of seeing this black word when you do a diffusive walk from, say, iPhone, maybe less than if you do a diffusive walk from iPhone cases, maybe less than if you do a diffusive walk from iPhones. And this difference in this changing of the trigrams is something that the attention model is able to capture, because the attention model takes into consideration all the other trigrams that you ended up visiting, and then it will decide, okay, you are probably thinking of an iPhone, and so this trigram is more important and that is less important, and that is what allows the attention models to handle this kind of a embedding task. And we have most of the proof, under these assumptions, we have most of the proof nailed down. And yeah, so we are finishing this work right now. That's ongoing work. Yeah, that's it. Thank you.
Any questions?
Yeah.
How was the query graph formed?
Oh, so we have data about query and products.
So it is through the product?
Yeah.
Query co-occurrence.
Yeah. So we have query product behavior data. So we know that if you search for a query, what products you bought.
Based on that, you
yeah, based on that. So the query is basically.
So but for the long tail products, you do not have those queries as nodes? Those queries will not occur as nodes? But those trigrams can come, that is the...
Yeah. So you have these query product behaviors, and for tail queries, you may not have a lot of products, or you may not even have seen that query at all. But the hope is that even if the data is sparse, you'll still see some related queries in terms of trigrams and so on. And that is what the graph captures. Yeah.
Any other questions? Okay, so then in the interest of time, let's thank the speaker again.